Hello everyone, let's solve another problem. Suppose T maps V to V is a linear operator with the property that T of V is equal to V for all vectors in the vector space V. If the vector V is not equal to the zero vector, show that V comma T of V is linearly independent if and only if T of V does not equal V and T of V does not equal negative V. Okay. So what I'm thinking here is we're going to start, of course, with writing down part of the definition of linear independence. And then I'm thinking like maybe we just apply T to both sides and see what can be said. Let me write down all the information we're given first. And see if I can't put together exactly what we want here. Okay, so what might be the best approach? I might have to mess around with a little bit of rough work here, and then I'll come back and see if I can put together the full argument nicely. Okay, so I've proven one of the directions here. I've proven that if this set is linearly independent, then we have these two inequalities both holding. The way I did this is first I supposed that T of V is equal to V. Then it's actually pretty clear that the set is not linearly independent because you have the same vector repeated twice in the set. Clearly if I just let A and B equal 1 and -1, then this is equal to 0 for non-zero A and B. Similarly, if T of V is equal to negative V, then you have two vectors in this set which are antiparallel, and that's not a linearly independent set. We can let A and B simply be equal to each other, non-zero, and then this is equal to 0. So if either of these are equalities rather than inequalities, then this set is not linearly independent, and logically that's the same as what I have here. So now I want to show the opposite implication, right? All right, and the second implication is also more or less straightforward and kind of corresponds a little bit more to my first instinct about writing down the condition for linear dependence or independence, and then just applying the operator T. So we're going to assume that the set is not linearly independent. This means that I can get this sum equal to 0 for I guess technically I only need one of A and B to not be equal to 0, but okay, I'm going to skip over the detail, the fact that one of these could be equal to 0, because that we should be able to prove pretty quickly that neither A nor B are equal to 0. Anyway, we have this rearranged to get the following. If we assume A is non-zero, then we can divide by a like this. We apply the transformation to both sides, and using the property that's given about this operator t, this t of v is just equal to v like this. And then rearranging this equation, we get that. So we have v written in two different ways. We have it written like this, but we also have it written like this up here. If we set these two things equal, this says that a over b is equal to b over a, or a squared equals b squared. And so a and b have to be equal to, I guess that's not true. They don't have to be equal to 1 or negative 1. They have to be equal to, I need a is going to be equal to plus or minus theta, and b is also equal to plus or minus theta for some real value of theta, non-zero. But that's fine, because we're going to divide this thing out anyway. So no matter what combination of b over a, of b and a you choose with the positives or negatives here, this is going to turn into either 1 or negative 1. So t of v has to equal v, or t of v has to equal negative v. And that's exactly, we're assuming the opposite of our given statement, and we prove the opposite of this thing that's implied. So in total, we have that if t of v is not equal to v and t of v is not equal to negative v, then this pair is linearly independent. Yeah, the only little thing would have to show here is that both a and b are not equal to 0. I've assumed they're both not equal to 0, but the definition of linear dependence says that they're not all 0. So let me see if I can prove they're both 0. Okay, and we're done. So we have this where at least one of a or b is not 0. We're going to assume that it's a that's non-zero, which means I can write v as negative b over a times t of v. Okay, we're also given that v is not equal to 0. That's given in the question. So I can write this, right? T of v is equal to v. We know that's not equal to 0. But that means that t of v is not equal to 0. Because if t of v were equal to 0, then t of that is equal to 0. Okay, so t of v is non-zero. That means, so this is non-zero. Actually, what am I doing here? We know v is not equal to 0. We don't really need all this. Right, so then clearly we have that t of v is not 0 and b is not 0. Right, if that's 0, then that's 0, contradiction. And if that's 0, that's 0, contradiction. Great. So that's supposing with a not equal to 0, but we can do the same thing immediately. We could have assumed that b is non-zero, and then we just transform this equation, right? av plus b t of v equals 0. Take t of both sides. And now we just get back to the same equation with a and b interchanged. So now we can assume that b is non-zero, repeat the same argument, and we get that a is non-zero. So that kind of ties up the loose end of what I had started with at the top here. Yeah, this is kind of a cool problem. It's not a property of linear operators I'd known about or thought about or come across. And my first instinct did eventually pay off here, namely that we wanted to write down something like this and then apply t to both sides of this equation and use the property that we're given for t to also get something. And where did I do that? I did that and going from this line to this line, basically. Yeah, if I have any more to say about this one, I'll put it down in the description. Otherwise, thanks for watching.